Happy Wednesday, everyone. We're going to talk about starting our new unit, universal gravitation and orbits. To start this, we're just going to talk about universal gravitation. The idea is real simple. Universal gravitation just tells us, universal gravitation tells us that any two objects with mass in the universe exert a force of gravity between one another. Now, just a reminder, Newton's third law, it's going to tell us that that force of gravity must be equal in magnitude, but opposite in direction. So even if we're talking about something like the Earth and the sun pulls on the Earth because the sun has mass and the Earth has mass. Likewise, the Earth pulls on the sun because the sun has mass and the Earth has mass. Now, which one pulls harder? Does the Earth pull harder on the sun, or does the sun pull harder on the Earth? And the answer is obviously they're the same because of Newton's third law. They must be equal in magnitude, but the Earth is pulling the sun in one direction while the sun is pulling the Earth in the opposite direction. Namely, they're pulling towards each other. Now, there's an equation for universal gravitation. So we'll go ahead and start with that. Fg, force of gravity. I'm going to use a big G because I'm talking about universal gravitation. G m1 m2 over r squared. All right, so Fg, that is your force of gravity. Force of gravity is measured in newtons. Big G, that's 6.67 e negative 11. This is a constant. It's on your equation sheet. M1 and M2, that stands for the mass of objects 1 and object 2. They have to be in kilograms. And R is the distance between the two objects given in meters. You may be saying, why is it R instead of D? It's because this equation comes out of calculus, and in the calculus conversion, or not calculus conversion, in the calculus proof, you end up with like a radial component, and that's why we end up having an R. For purposes of this class, that really doesn't matter. Just know that R is the distance between the two. It's a real simple equation to use. Here's a block, and it's 5 kilograms, all right? And here's another block, and it's 10 kilograms. And these two blocks are put 40 centimeters apart. So your goal is, well, what's the force of gravity between them? And in the process of solving for this, you'll see why we have never cared about using this equation before. If you think about the force of gravity on the 5 kilogram block caused by the Earth, it's just shy of 50. And as for this one, it's just shy of 100. Well, what about the force of gravity that these two exert on each other? That's 6.67 e negative 11. That's a very tiny number. And because it's a very tiny number, it's going to result in a very small force of gravity. Please note, 40 centimeters, we have to convert that into meters, so we'll do 0.4. Now is the point where we grab the calculator, punch in the numbers, and see what we get. I got 2.08 e negative 8 newtons, or about 21 nanonewtons of force. So the Earth is going to be pulling on these objects with about 1 billion, about 10 billion times the amount of force as they're pulling on each other. And that's why we don't really witness it. This becomes a much bigger deal, though, when you start talking about, that was from my other class. When you start talking about things like, here's the sun. And the sun is going to keep the Earth in orbit. So this is where universal gravitation is going to become important because, as I said, this unit, universal gravitation, and orbits. So what's the force that's keeping the Earth in orbit around the sun? The force of gravity, which is why we needed universal gravitation. So that way, in a future date, we can describe orbits. It's a real simple concept. You have a web assign on it tonight, practicing using this force of gravity equation, and that should be a wrap for today. Your tests hopefully by the end of the day, Wednesday, if not Thursday or Friday.